Good afternoon, everyone. My name is Jeff Klein. I'm the Director of Structural Engineering for VHB in Providence, and I'm the President of the Rhode Island section of ASCE. Thanks for joining us. Today, we're joined by Ethan Martin. He's going to be presenting his topic on tall mass timber construction and carbon footprint reduction. A little bit about Ethan before he gets started. Ethan's a problem solver by nature, which tends to have him challenge the status quo. To try and design things a little better, a little more efficiently. He has a passion for sustainability of wood design, and use that in his role as Northwest Regional Director at Woodworks to start the International Mass Timber Conference with Forest Business Network. He's a firm believer of thinking outside the box, especially when it comes to mass timber design, and his topic's going to be a deep dive into that idea. So without further ado, I'm very pleased to introduce our speaker today, Ethan Martin.
All right, thanks, Jeff. And so, yes, as Jeff mentioned, I started a lot of wood buildings and things like that, and we'll talk on that. But right now, I am at DCI Engineers, and we're starting a mass timber division, and basically balancing what DCI has already done over the years. And if you've not seen us, we've got about 350 employees. We've got 13 offices. We're mainly West Coast, Midwest. We are doing some projects in the Northeast there, and we've got a project in South Korea, and we're actually doing 11 of these new tall Type 4 mass timber buildings. And so we'll touch on that. And I will apologize that this presentation, funny enough, is difficult. To cover carbon and wood, and then cover life cycle assessment, and then cover the tall wood buildings. That's a lot to put in an hour. So I'm going to be running at about 100 miles an hour, but feel free to ask questions, or feel free to wait till the end to ask questions. But this is just some of the stuff we've done at DCI. Again, we've got about 60 projects now out of mass timber that we've completed. And, from everything from office space on the left-hand side here to this is actually a WeWork space on the right-hand side. That's a flat iron building. On the left-hand side here, you'll see this is a office space for an architect. On the right-hand side is the Bullitt Center in Seattle. That's one of the first Living Building Challenge buildings in Seattle. And so my background is, structural engineer, and had my own company, was designing a lot of wood buildings, and then went to work for the wood industry to promote wood construction. And I come at that from a sustainability standpoint, but I'm the one that started these tall mass timber buildings. I set up a prescriptive performance-based process through the governor's office here in Oregon that had a guaranteed building permit. So the idea was you could get a developer incentivized to go in because they could spend this time and effort, and they knew they were going to get a building. It wasn't like, hey, we're going to spend all this time trying to do a prototype building, and the building department may say no at the end. So the guaranteed building permit was really critical in that. And then I helped D.R. Johnson become the first manufacturer of CLT for buildings. And that we'll talk about what CLT is in a minute. And that was also through the governor's office. So definitely a sustainability person, definitely interested in wood and mass timber. And so we're going to try and cram this all into an hour here. So the difference between mass timber and light frame construction is that mass timber maintains its internal temperature in a fire event. It's got such a large volume of timber versus surface area that it chars versus rapidly combusting like light frame construction. And so what you'll find here is that it's predictable, it maintains its shape, and it's a really different animal in fire design than light frame construction. And we'll talk about CLT, DL. So CLT is cross-laminated timber, DLT is dowel-laminated timber, NLT is nail laminated timber, NPP is mass plywood panels, and obviously you guys have seen lots of glue lams also. So there's a lot of products that fall into the mass timber as long as you finally get that large, volume of timber versus surface area that it predictably chars. And we'll talk about some of the sizing of that later on. So why wood? Wood, as that tree, takes carbon dioxide out of the atmosphere, while it takes, sunlight, while it pulls up nutrients and water out of the ground to form that cell, to form that lignin, 50% of that wood fiber is carbon. So to grow that tree, it is removing carbon dioxide and taking that carbon and forming the wood cell and then releasing oxygen, O2. So wood basically is a carbon sink. And we'll talk about why some people want to look at the growth of trees being a carbon sink and some don't. But what we've got to look at as structural engineers is that the manufacture of the building materials that go into our buildings, right now it's about 11% of our total global greenhouse gas emissions. And obviously you guys have probably seen the political stuff going on with our new president and getting back into the Paris Climate Accord agreement. And basically that's trying to minimize the temperature rise across the planet. And obviously global greenhouse gas emissions play a critical role in that. So where we've been, this is a more recent chart here, basically of 2017. And really we've been focused on embodied carbon. That's the AIE 2030 challenge, focused on this on the building operations is the AIE 2030 challenge there. And so you'll see this is as of 2017. Even back in about 2014, building operations was about 84% of the carbon dioxide emissions. And so even just between 2014 and 2017, this has dropped from 84 down to 72. And thus, obviously, embodied carbon starts to play a bigger and bigger role. So again, AI 2030 really been focused on the operational energy. The new ASCE 2050 challenge for structural engineers is really how do we reduce our embodied carbon? How do we reduce the material impact going into the building? And if we meet this challenge, the idea is by 2050, 50% of your carbon dioxide pollution will be from the operational energy, the AA 2030. 50% of the building carbon dioxide pollution will be from the embodied energy. That's the intention there. And so what does that mean in real life? So here's a building that Skidmore, Owings & Merrill did back in about 1960, a concrete building. And they said, hey, what happens if we go and switch out all the concrete we did and put in a concrete timber hybrid system? What would that do to our carbon pollution or reduce embodied carbon? And it dropped it down from 100% down to 41%. And this is not even considering third-party certified wood. This is just using wood. And so the deal here is to keep an eye on this. This is 41% just using wood. You use like a third-party certified wood from a managed forestry program, and this actually dropped down about 16%. So it's a significant impact that we can make by changing building materials. And so people go, oh, well, you're cutting down all the trees, you're gonna kill us, it's gonna destroy the planet. This is deforestation. What you're seeing on the screen is deforestation. You're removing the forest. So here you can see the forest in the background. This is a solar farm near Atlanta. And you've removed the forest and you've put in another use. And that other use does not change back to a forest. You're not going to naturally have trees growing here anymore because you're trying to gain that. That's not what we are talking about. We are talking about a crop where we cut down the trees, we replant the trees, and you just keep a crop rotation going, just like a farm. You grow the corn, you cut the corn down, you replant the corn, you grow the corn, you cut it down. And trees are very similar. We're just on a much larger harvesting cycle of about 50 years-ish. And so here's some of the devastating facts that you're seeing. In North America, we're burning about 3 times more forest than we're harvesting. Our forest area, and we'll show some tables on this in a second, but our forest area is increasing about 2% per year, but the volume of trees on that forest area is increasing by about 5%. And that's leading to these forest fires we're having. And then you look at how much forest we utilize in the US, and we use less than 2% of our forest area in the US. And you look at Austria, look at Germany, they're utilizing like 35 and 45% of their forest area, a much, much higher utilization rate than we are. We're only down here at 2%. So there is no concern in North America about hurting our forests. And environmental groups get all over that, but that's not something we really need to be concerned about unless we start hitting that 45% utilization rate. And so again, we've held steady at this number for years and years and years. And we have forest practices, state forest practices, tribal forest practices, federal forest practices that require mandatory regeneration. So if you cut down the tree, you've got to replant 3 trees. And I looked at the Northeast, and private forest land is about 89% across the country, And the Northeast, it's down to about 81%. Private forest landowners own about 81% of the lands in the Northeast. And then this is Oregon, so I'm out of Portland, Oregon. And here I don't know if you guys saw it, but I'll show you a pretty picture in a minute. Last year, we had out of control forest fires, like literally out of control. We could not put them out. And they killed about 15 billion board feet of lumber, which is about 1 million homes. And so the sad part about that is, okay, the trees are done and gone. But now the problem is we got to go replant. And it's going to take another 50 years for that 1 million home quantity of lumber to come back, because you got to replant the tree and you got to wait 50 years. So that's the devastating thing that we're seeing with the forest fires. And so this is the table. This is the graph, the technical data showing you this. Here's our forest area. So this is the land that we have to grow trees on in the US. You can see Industrial Revolution here, where we had farmland get developed, we had pasture land get developed. But since that has happened, we've stayed pretty steady on forest area. But this is the problem. The problem here, this is the volume of trees on that same land. And you can see here it's increasing. And the problem with that is you get these really dense forests and you get these really weak trees. And we'll show you the healthy tree scenario in a second. But this was 2014. So we knew this was coming. They're showing here on the left-hand side of the US here, all this red, fire hazard area, southern Florida fire hazard area, even some here in North Carolina, South Carolina fire hazard areas. And then here comes along 2020, and this was the map of the fires. Look at this, out of control, could not put the fires out. A bunch of fires going on in Colorado, and also, Idaho and Montana were going on, and then down in Florida. So we mapped this out. We knew this was going to happen. So that was in 2014. They warned about it. Here we are 6 years later, and it's out of control. We could not put the fires out and just had to let them burn. And so what you're seeing here, this is not cloud cover. This is the smoke from those forest fires, all the way up from Northern California going up through Oregon here. And this literally got all the way over to France. And if you don't think that's a problem, that we're polluting the entire planet through forest fires, we've got some issues. So, I joke, but it's a problem. And it needs to be addressed. And not only is it affecting our atmosphere, but it's also affecting our drinking water. Because what happens in these fires is that you'll get this, fire, and if it gets really, really hot, it will burn down all this organic rich soil. It'll burn down this water repellent layer. And so then when it rains, the water just grabs all the ash and everything and pours it into our reservoirs. And that actually happened in Denver. So Denver actually was spending lots and lots of money trying to get the ash and everything out of the water supply that's feeding the city of Denver. Utah and Nevada, exact same problem. They've got, same thing, forest fires going in and polluting their drinking water. So it's a little bit of everything. And so, what's managed forestry and how does that define us in green building programs? And a lot of people, I will say, have been misled by third-party forest certification programs. And so we'll talk about that. So this is one of our East Side Washington healthy forests. And so what you see here is the trees are well spaced. Each tree is getting lots of sunlight. Each tree is able to grab a lot of water out of the soil around it, able to grab all the nutrients out of the ground around it, and it creates a really healthy tree. If you get these dense forests, they're all fighting for nutrients. They're all fighting for sunlight, and you'll get like 20 weak trees instead of 5 healthy trees. And that's where the pine beetle is killing them, because the pine beetle won't kill a healthy tree, but the pine beetle will kill the weak trees. And that's where you're seeing the forest fires too. You got these really, weak trees that have a lot of dead limbs, and that, increases the fire. So, wood is the only product that has a third-party certification system attached to it through FSC, SFI, PEFC, Canadian standards, and then ATFS is the American Tree Farm System. So this is like the American Tree Farm System is like mom and pop. PEFC is a global thing. FSC and SFI are somewhat less global, but still global. And, a lot of people are like, oh, well, that's great. Look, they're, SFI is doing 300 million acres. And, FSC is doing 320 million hectares, which is, I think, about 180 acres or something like that. And these graphs are deceiving because these graphs, you kind of go like, wow, FFC's got all this covered. No, this is about 22%. If you actually drew this as 22%, you'd see a little blip over here that they have certified forests. So these graphs, these images they promote are a little deceptive in that. And then you'll find that a lot of this is managed. This is managed by state regulations. This is managed by tribal regulations, US Forest Service regulations, and we don't have to be adding on the additional cost of third-party certifications to get a healthy building using healthy forests. And so this is a forest right by my house. I hike this trail on a regular basis, and this is overgrown. But luckily, this is a low-intensity fire, so you can see the greenery is still up here at the top. Obviously, killed all the underbrush here and everything, and killed the lower branches of the trees. But this is too dense. This is too many trees. They're not getting any sunlight in here. You can see, look, a little sliver of sunlight, a little sliver of sunlight. And so they're all fighting for water. They're all fighting for sunlight. They're all fighting for nutrients. And this is what happens. These fires get out of control. They hit about 3,000 degrees. And at 3,000 degrees, that's when you burn all the nutrients out of here. And when you burn those nutrients, you saw me say earlier where it'll take about 50 years for this forest to come back. If these out of control forest fires hit that 3,000 degree mark, they burn the nutrients in the soil and then nothing grows back. Even if you went in here and planted trees, they would not grow because you've now cooked all the nutrients out of the soil. So the point here in the mass timber is, how do we thin these forests? It's not about clear cutting. It's about how do we go thin these forests. And so this is Boggin Timbers up in Washington. And basically what we're doing here is small diameter, 6-inch, 8-inch diameter logs. So we're not talking old growth. We're not cutting down the 3-foot diameter trees. We're not even cutting down 18-inch diameter trees. We're getting that we're thinning these forests out. We're taking the small diameter, We're taking the small diameter, 6-inch, 8-inch diameter, thinning the forest out to let this tree keep growing, let this tree become healthy, strong, get all the nutrients, thin this tree away, hopefully before the forest fire. And put that, make this into boards, make it into a product. So what you're seeing here is a cross-laminated timber panel, made at Boggin Timbers. So taking that small diameter, putting the boards in there. Here's a glulam they made up, again, small diameter, but taking that small diameter and making large format mass timber products. Or again, we can just keep burning it. And again, that to me is out of control. Like, that should not be happening. We've got a problem that needs to be fixed. There's San Francisco on fire. Here's one of our projects right up against a fire in Oregon. And so this is where I'm going, like, stop burning the trees and start, manufacturing mass timber products and put them in a building. So these are glulam columns and glulam beams and CLT floor plates going in there. So how do you start doing that as an engineer? And this is a service we can provide to architects. Architects are doing it also. But life cycle assessment is a process, and a process to study and tabulate the environmental impact of the materials you choose. So you have to kind of define, like, okay, how do we want to measure this? Do I want to measure this from cradle to gate or cradle to grave? What do we want to count? Do you just want to count the beams and columns, or do you want to count the beams, columns, hardware, expansion anchors, whatever it is? And then you've got to pull all the data for that, stuff it all in an Excel spreadsheet or whatever you want to do, and then report out your results. And so cradle to gate is this A1 to A3 is really, okay, getting this material out of the forest, transport it, manufacturing into a product. A4 to A5 is the construction process. So, okay, I've got these glulams made up. Now I'm putting the glulams in the building, and it sits there and it lives its life. In the B1 through B7, there might be some repair replacement, but the big chunk of your LCA is typically going to be in this A1 to A5 stage. A lot of people do A1 to A3 and kind of stop from the product getting manufactured. I do argue that you definitely should take it to the A4, A5 because this transportation can play a huge role in this. And so I'd recommend at least do an A1 to A5 in here. B1 to B7 repair maintenance is there, but it's not a very big thing. And then the end of life. what are we going to do with these products after the building gets torn down? And a lot of people are like, oh, I need a building that lasts 100 years. You can pull up the data on this. The average lifespan of a building in the United States is about 28 years. The use changes. A new tenant comes in. How many of you guys had laptops when you were in school? I didn't have a laptop when I was in school. Now everybody's got laptop, and they need an electrical outlet at every single table, every 2 chairs. And so the use changes, and that's why people tend to tear the buildings down, is because the use of the building changes, and they just can't utilize the structure anymore. And so a lot of people say, like, whoa, well, where's all this data for end of life of mass timber buildings? It's like, we don't have enough mass timber buildings to actually have developed a company that specializes in this demolition. So are we looking at deconstructibility? Yes. Can these mass timber commercial buildings then become, like, say, a residential building? Yes. Can it go into a shredding process and become toilet paper? Yes. Or can you just, dump it in a landfill, which is not what we want to do. But that's the process. We look at kind of the whole life cycle of the products that are going in there. And there's easy ways to do it. You can do an Excel spreadsheet on your own as an engineer, and get some EPDs. The EPDs is an environmental product declaration that has a bunch of information, and we'll show you some of that. You can go super simple. Tally is a plugin for Revit. So, and this is something we're using at DCI, is like, basically we're building our model in Revit. This Tally plugin actually creates the LCA for us, and then spits out all the results for us. Athena Sustainable Materials Institute has several programs of a whole building analysis. So you can literally put in there, hey, I'm doing a 6-story building. What's my environmental footprint? You can also go like, okay, I'm going to put in the major components, and it'll give you an environmental footprint. Or some of them is like, I want every single item that's going into the building, and it'll give you an environmental footprint. But again, that goes back to, at the beginning, you've got to define your boundary. How much do you want to measure? And with that comes a fee. As structural engineers, what's our fee for that? And so, if you got a client that says, like, look, I just want the pat on the back, I want to feel good, there are definitely some black boxy programs where you can literally just put in there, I'm doing a 6-story building, I'm using wood, and it'll spit out an answer for you. And then obviously there's the Tally plugin that's measuring every single item that we're putting in that Revit model. And our fee on some of those projects might be $60,000. There are clients that want to measure the environmental footprint from the manufacture of the product all the way through to the buildings constructed, and with a future plan for deconstructibility. We do have clients asking for that. So this is where wood has an opportunity here. So this is from Arup. If you've not seen Bruce King's book, Bruce King, I worked with Arup to help him write that book. But basically, this is growing to show you got some energy here. You got to go out there, you got to drive a truck out there, you got to send a human out there to plant the tree. So there's a little carbon dioxide pollution to plant, but then you've grown this tree from anywhere to 30 to 100 years. I would say usually the average is about 50 years, at least on the West Coast. And that's, again, it's sucking the carbon dioxide out of the atmosphere, it's storing it in the wood cells, and then again, you've got to go make a product. So you go make a product, and then you go put it in a building for its life cycle, and then it's like, what do you do? If you just incinerate it, even if you put it in the landfill, this will eventually come back up to zero here, or can you recycle and reuse? So this is wood, and there's a bunch of programs to model the environmental footprint, but here's my note of caution. Some programs do not account for this growth and the sequestering of carbon, and some do. And so again, if you don't take into account this growth here, then wood's going to have to manufacture the product and have it in a building. It's going to have a positive impact on the environment. I will still argue, if you actually overlaid concrete on here, concrete's going to be way up here. Steel's probably going to be right around here somewhere. So you're still better off, but you'll still get a better bang for your buck if you take into account the sequestration of the carbon dioxide out of the atmosphere when the tree is growing. So what's an EPD? The EPD is the Environmental Product Declaration. There's a lot of people making these. And basically, it's a documentation of the environmental impacts to make their product. So here's one for glue laminated timber. Here's one when we did for cross laminated timber with Quorum and University of Oregon and Oregon State University. And basically, what it does is it says, okay, cradle to gate. Cradle to gate is, again, making the product in the forest to manufacturing the product as it's sitting there in the manufacturer's facility, not to the site. But here's the deal. It's like, okay, what did it take to go manage that forest? You know, you had people driving out there, you had logging operations, you had planting operations, you know, then you had to go get the tree out of the forest, you transported it to a mill, mill cut it up, they had to dry it. They then made a product out of it, they finger jointed it, they glued it, and then it's sitting in, the shop at the end. And so this is what the EPD is doing. And in that process, it is measuring things. It's measuring global warming potential, acidification potential, eutrophication potential. So this is like, air quality. This is stream quality. This is acid rain quality. This is carbon pollution in the atmosphere. And so they have all these different things. And so with what you can do with your EPDs, you can say, okay, well, I've got 40 million linear feet of glulam, 40 million linear feet times this number, 40 million linear feet times this number, 40 million linear feet times this number. And then you can say, and then I've got 10 steel beams, and 10 steel beams times this number times this number. So you'd be using this for glulam, you'd be using the steel beam one for the steel beam one. The only downside to EPDs right now is they are governed by the industry that manufactures the product. So the wood industry determines what they want to include in their EPDs. The steel industry decides what they want to include in their steel EPDs. And so you're not going to get 100% apples to apples comparison, because you might find out the steel industry does not take into account non-renewable materials, where the wood industry does. These first, 5 right here, yeah, you'll find the first 5 here that steel industry, concrete industry, wood industry does have information on these. But on this other stuff, you may not be able to do an apples to apples comparison, because that industry may have decided not to measure something. So that's the only downside to the EPDs. But again, it's creating this database here of, okay, what did it take in forest operations? What did it take to make the product? And then here's the total EPD, cradle to gate. What is all the environmental impact that went into that product to make it? And so, as I touched on, not every project has the budget for a whole scale or a full scale whole building WB LCA's whole building LCA. Again, there's people that just want a pat on the back. There are programs out there you can buy that can actually help you do a whole building LCA, but there's not every project has that budget. And that's just definitely something to discuss with your client. And then I fully argue that specifying responsibly managed wood is a much more effective system versus proprietary third-party certified wood. And don't get me wrong, these guys are doing a great job in areas like South America or Russia that are going through their kind of industrial revolution on the forestry side of things. And North America, my personal opinion is that it's just adding costs to the project, and it's not actually doing what you think it's doing. Specifying FSC is probably not doing what you think it's doing. FSC cannot be applied to a thinning of a forest. So again, I talked about this thinning and getting that small diameter fuel load out of the forest so we can reduce these forest fires, and you can't get a thin forest FSC certification. So everybody thinks FSC is the bomb on forestry certification, and it doesn't apply in certain situations. So then tall buildings. Yeah, so now we're going to jump into tall buildings, but there is a question on species. So Chad, what's the question? Let's see. So Chad, oh, here we go. Is there a certain type species of wood that is in more high demand in construction? Does a monoculture of trees help or hurt land in a region to erosion and fire prevention? So it's almost 2 questions there. So the beauty of the wood industry is they have a lot of performance specifications. And what that allows each region of the country to do is utilize the species that's more prevalent in your area. And so that's I think, a benefit. So here in the Northwest, say Washington. Washington is a bunch of spruce pine fir. We've got a boatload of spruce pine fir, so we're using spruce pine fir a lot. Oregon has a lot of Douglas fir, so we use a lot of Douglas fir out of the Oregon region. Southeast, you got the southern yellow pine, and that stuff grows like weeds. So use the southern yellow pine. There's no point in shipping southern yellow pine all the way to the Pacific Northwest, because again, that trucking will destroy your environmental footprint. So no. The beauty of the wood industry is that there isn't one species that is in more high demand in construction. The stronger woods, the Douglas fir, the spruce pine fir, the southern yellow pine, I will say are the most common for blue lambs and for the heavy timber members. But there's actually people looking at hemlock right now. It's like, can we start using hemlock, which is really kind of a low quality wood? So there are the current drivers, but there's nothing stopping us from looking at a different species. And then does monoculture of trees help or hurt the land? And I will agree that it hurts the land to have some of these monocultures. But if you spend enough time in the forest, the monoculture really happens on the plantation side of things, and not so much, especially in the Pacific Northwest, not so much. You go into a forest out here that has been planted with, say, spruce pine fir, you'll actually get in there and there's Doug fir interspersed in there. There's, deciduous trees interspersed in there. And you'll find that, people say we have a monoculture out here, but in reality, we don't. But you will definitely find a monoculture in plantation kind of forestry. And so, yep. Okay. So with that, if that answers those, we will get on with the tall buildings. So the tall buildings, if you've not seen this, there are new construction types in the 2021 IBC. And what they did is they basically said, let's add 3 new construction types. Let's not adjust anything. Let's not change anything. Let's add 3 new construction types. So we've had that type 4 in there. There's now type 4A, type 4B, and type 4C. And what it is basically type 4A is 18 stories, all encapsulated. You won't see the wood. This is based on Brock Commons in British Columbia. And this is framework. So this is the building that I got this building permitted and this building permitted here in Oregon. And so this is framework here in Portland. So they're modeled after prototype buildings. So this is Brock Commons in British Columbia, the 18-story building. This is framework here in Portland, Oregon, the 12-story building. And this is Carbon 12 here in Portland. And it's 8 stories of residential. So the difference between these is the 18 stories, you won't be able to see any of the mass timber. Smoke is what kills people in fires. So this, you're going this tall, it's life safety, you want to get the occupants out of there. And so you're covering up all the wood because even though it chars and it's predictable and it maintains its shape, it still produces a lot of smoke, and smoke kills people. So the 12 stories then has some allowances. You can have 20% of the ceiling exposed, or you can have 40% of the walls exposed, or you can do a combination of that. And you guys on the East Coast are lucky because in high seismic, we won't have mass timber walls. There's no ductility, no energy absorption for the high earthquakes. And so we, funny enough, won't have a lot of walls in our mass timber buildings on the West Coast because we can't absorb that much seismic energy. Whereas the wind energy, the wind just leans the building over and comes back, remains elastic. And so you guys you'll be lucky because you'll have walls and roofs. And so you can have the 20 of ceilings, 40% of walls, or a combination of that, X over 20 plus X over 40 as the combo, less than a unity equation of 1 in there. Or you can do this type 4C, which is all exposed. All this mass timber can be exposed, but you're still limited to 85 feet in here. So that's the new. And then this is the traditional type 4 heavy timber that's been in the code now. So what they've done in the code is this now is labeled type 4 heavy timber. This is labeled type 4C, this is labeled type 4B, and this is labeled type 4A. And so again, since I worked on these buildings here in Oregon, I got this adopted early in Oregon code-wise in 2015, got it adopted in Washington in 2015 also. Utah followed suit in, I think, 2017. City of Denver got this adopted in 2019. And then California, it's already gone into effect already. We got 2 buildings. We're already permitting 2 of these buildings in San Francisco right now, using this new code in California. And so this is just the breakdown of it. For these occupancies, 270 feet, 180 feet, 85 feet, the number of stories associated with the different occupancies, and the allowable area per floor. So it's pretty good. The only note, a caveat I will toss out in here is that at 120 feet, you have to use the high-rise sprinkler requirements. In steel and concrete buildings, that doesn't kick into about 400 feet. In these mass timber buildings, the high-rise sprinkler requirements kick in at 120 feet. So you get over 120 feet in 4B, you got to use the Chapter 4 high-rise sprinkler requirements. In 4A, you're definitely going to be using the high-rise sprinkler requirements for any building over 120. And so again, so this is just for you. A lot of building officials will ask, like, hey, how do I do these char rate calculations? These new building types have 2-hour ratings. And again, the IBC only allows us to calculate 1-hour fire ratings. And so everybody's like, well, how do I get the 2-hour fire ratings if the IBC only lets us do, 1-hour fire ratings? And so here's the code path. 703.3 says you can, do several methods for fire calculations per 722. 722.1 refers to the NDS, and NDS Chapter 16 has char rate calculations for up to 2 hours. So it's a process. And so if you got a building official that's giving you any grief on that, this is the process. You go to 703.3, 703.3 references to 722, 722 references the NDS, and Chapter 16 of the NDS allows you to do 2-hour char rate calculations. So not super straightforward, but it is what it is. And so again, on these tall mass timber buildings where we've got 2-hour ratings, wood fiber costs money. It's not free. And so if you're going to need a 2-hour rating and it charges at 1.5 inches per hour, you got to buy 3 inches of wood fiber to be the exposed mass timber and be your fire rating. And that's a lot of money to spend to buy all that wood fiber just to do the fire protection. So, non-combustible gypsum protection can provide a lot of rating. Obviously, you won't see the wood. And there's definitely architects who are like, I've got to see the wood. That's what I want. But you can, we do have projects where we are encapsulating, say, the floor plates and leaving the beams exposed, or we're encapsulating the beams and leaving the floor exposed, trying to do the yin and yang of like, okay, well, let's spend some money on gypsum and some money on wood fiber. And, it doesn't have to be all exposed or all encapsulated. You can do the yin and yang of a little bit of both. But the beauty is it's predictable. It's 1.5 inches per hour. Again, the NDS covers this for you and has, char rate calculations and everything. The one thing for structural engineers to be aware of is there's a 0.3 inch. So a char is at 1.5 inches per hour, but there's a 0.3 inch heat affected zone in front of that char. And you need to make sure your connections stay out of that 0.3 inch heat affected zone. So you've got a steel screw in there and it's in that 0.3 heat affected zone. The steel screw will actually absorb heat and start charring from the screw inside out, and you'll lose your connection. So you definitely need to be aware of that. So this is just the table, is that basically the 4A and stuff, everything's 2-hour, 1 hour for roof primary frame. Floor construction stayed at 2 hours all the way across there, and primary frame and 4A went to 3 hours, and then 4B and 4C went to 2 hours. And so again, there are now some prescriptive tables in the code, which is nice. That basically says, okay, you want to do a 4B building and you're putting some, you need to have 1 layer of gypsum on there for 40 minutes, 5/8 inch type X. This is how you get there. So instead of you having to go to another table, there used to be some tables in the code that you would have to go to get to this. Now they've actually just created a table saying, okay, if you want to get, 1 hour rating, you can put 1 layer of 5/8 inch type X on it and then do the rest out of the char calculation. So this will get you 40 minutes. You do the next 20 minutes doing the char calculation of the heavy timber. And this is kind of what this looks like. It's like, okay, so primary frames, they have a 4A building. It's 3 hours. And it's like, okay, well, what do I want to do? Do I want to slap on 3 layers of 5/8 inch type X to get me 120 minutes? And then I need, so that's only 2 hours. Then get the 1 hour char rate calculation. Do I slap on 4 layers of 5/8 inch type X? And then I only need 20 minutes of char. So there's different ways of going about this. Same thing here on a 2 hour, say a floor ceiling assembly in 2 hour and 4A and 4B. Again, you can just slap on 2 layers of 5/8 inch type X and get 1.33 hours. And then again, do char the mass timber for 0.67. Or again, you can slap on 3 layers of 5/8 inch type X, get your 120 minutes out of it, and do 0. Or right down here, do 3 layers of 5/8 inch type X, and then do 0. And you don't need any extra wood fiber from the mass timber, which obviously wood fiber costs money. Oh yeah, so yeah, here's the fun part. So just what I was showing here. So say you've got a column in one of these mass timber buildings, and you slap on the 3 layers of 5/8 inch type X, and you're like, woohoo! Like I don't need any char rate out of the mass timber, and I can get a 4x4 wood column to calc. Well, no. The deal is, again, you need a minimum section size to maintain that internal temperature and to ensure the member chars. So even if you put the 3 layers of gypsum on it and you only needed a 4x4 by calculations, you still, whoops, where did it go there? You still, gosh darn it, what is it doing? Sorry, my slide thing's jumping all over the place. You still have to meet the code minimum section size to be considered a piece of heavy timber. So that's where we as structural engineers, we have to be involved with the architect early on when we're talking about this, and with the contractor when we're talking early on, because you might say like, oh, well, let's just slap on the 3 layers of gypsum. We don't have to worry about any char rate out of this. I only need a 4x4 column. Well, now you go to this table, you're like, well, crud. By code, we need an 8x8 column to be considered heavy timber, or actually in glue lamb, 6 3/4 by 8 1/4. And you're like, well, crud, this already gives us 3 inches char on this side. It gives us 1 3/4 inches on this side. That can probably get rid of 1 full layer of gypsum. So now it's like talking to the contractor, and it's like, well, we said 3 layers of gypsum with no char, but we actually already have to have char per the minimum section size. Why don't we just use 2 layers of gypsum and take the char, because we don't need the rest of this wood member for structural reasons. So that's again, it's a conversation. That's why you actually need to be a bit more involved in these projects. And I do see some more questions come in, and I'll jump on those here at the end. So 4A is, again, based on Brock Commons here in British Columbia. So I helped on this project a little. And I don't know if you guys follow this. This is 17 stories of mass timber over a 1-story concrete podium. And it has a panelized exterior rain screen wall system. And then it's just posts and plate. This is glue lam columns and a CLT, cross-laminated timber floor plate. There's the piece of cross-laminated timber right there. And craned in, each corner of the CLT sits on the corner of this column here. And if you didn't follow this, they basically, I sat down with the installer on this and the university and some people, and we were kind of hashing out like how long would this take and everything. And it was funny because guesstimated and Structurecraft did an amazing job on this. The Structurecraft estimated they could do 17 stories with this building envelope in 18 weeks. And if you didn't follow it, they finished in 9.5 weeks. So this mass timber, one of the reasons why we're going after this mass timber is that speed of construction. And I've not had a contractor that I've worked with out of like the 30-something contractors I've worked with that has estimated that properly. It's just amazing how fast this goes. And it really, that speed of construction, you got your tenants in there occupying the building. They're paying back the developer on, return on investment kind of thing. So there's a whole bunch of hidden benefits with that. But so this is it, 270 feet, 18 stories of mass timber allowed. But again, you won't see any of the mass timber. This will be all encapsulated. 4B, again, based on framework here in Portland. We were trying to do a rocking wall system in here, and this project may get built at some point. It fell in some new market tax credit stuff is the only reason, but we got our permit. What was that? June of 2016 or 2017. So this was permitted and ready to roll, and then their financing that they were using to finance the building kind of fell through. But so 12 stories, again, 20% of the ceiling can be exposed, 40% of the walls can be exposed in there. And again, you can also do the unity equation. So again, if you want some of the ceiling exposed and some of the wall exposed, it's x over 20 plus x over 40 less than 1.0 as a unity equation. And again, we really won't have walls in our high seismic area on the West Coast here. The thing to be aware of in the type 4B is if you have a column, say you've got a column that's on the exterior wall of a CLT wall, that is considered integral. And that goes towards the calculation of your 40%. And what cracks me up is this is still being worked out at the code level. And I went to the code council and I was asking some questions and stuff. I'm like, well, when is a beam can we leave all these beams exposed and then just encapsulate the floor? Because, you know, the beam is really not integral to the floor if this floor is encapsulated. And they're like, yeah, that's exactly what we thought. And then about 3 months later, they called me back and they're like, nope, actually, nope, that wasn't what we meant. We got to retract our statement. And so again, the code is here, the code's been developed, but there still are some gaps and still some misunderstandings happening out there. And so what they decided was that a beam, the beam supports the floor, then it's integral. And I was kind of like, well, when would a beam not support a floor? So there's some code language in there and there's some things in there. But basically what they've said now is that this beam and this floor counts towards your 20%. And what I will caution is this surface area on a beam on 3 sides adds up really quickly to 20%. And so we've got projects where we're encapsulating the floor system and getting our 20% just out of the beams. And we have projects where we're encapsulating the beam and leaving the mass timber floor plate exposed. But the beauty here is this interior column then is not integral. It's not integral because it's not attached to a wall with CLT or MPP or whatever it is. And so all your interior columns can be exposed. But again, when you've got a 2-hour rating or a 3-hour rating, you're buying 3 inches or 4.5 inches of wood fiber on each side. So that column needs to grow by 6 inches in a 2-hour fire rating. And it's like, whoa, do we really want to buy that 6 inches of wood fiber? Because wood fiber costs money. So we do have projects, funny enough, we are in a 4B where this can be exposed and we are fully encapsulating the columns just because the wood fiber is more expensive than buying gypsum and applying the gypsum. Yep, so that's what we talked about already. And then 4C, again, it's based on carbon 12 here in Portland, all exposed. Again, the downside, so funny enough, this building's 108 feet high, but through the code hearing process at the ICC level, they only let this go to 85 feet. But the beauty is everything can be exposed. Your columns, your beams, your floor plate, everything can be exposed in there. But again, 85 feet. And so one of the reasons why people didn't pick type 4C, people didn't pick type 4 back in the old code was you weren't allowed to have enough concealed or any concealed spaces. And the reason behind that is if in this cavity, if you had enough oxygen in here and you dropped a ceiling in here and say you had a piece of conduit that was like shorting out, you'd never see it. And again, the mass timber chars versus combusting and catching on fire. So if you had an electrical conduit in here that was shorting out, it would smoke and smoke and smoke and never catch on fire with just enough oxygen here. So basically type 4, you were not allowed to have concealed spaces. That's one of the reasons why a lot of people didn't pick, heavy timber construction as a construction type. Now with the new code, these tall buildings, you could do concealed spaces. And everybody went, well, wait, if in the tall buildings you can do concealed spaces, then why can't I have concealed spaces in the old type 4 heavy timber? And so the old school type 4, they created 3 new options for having concealed spaces. You can drop a sprinkler system in there. Don't have anybody wanting to do that yet. You can fill it with rock wool, mineral wool. Only have that where we've got like a resilient channel. We've done that in a couple of projects with a resilient channel. And it's a little thin layer of rock wool in there. What 90% of our projects we're working on right now, people are just slapping on a layer of gypsum. You got a drop ceiling in the bathroom, drop ceiling in the kitchen, just slap a layer of gypsum direct applied to the mass timber. That is one of the caveats. You can't have resilient channels, then this gypsum. This gypsum has to be direct applied to the mass timber. Again, if you had resilient channels in there, you'd have a cavity for oxygen. So the idea is to get rid of that oxygen in there so the fire can't combust. And so the tall buildings, this is what they did. In the tall buildings, type 4A, 4B, 4C, basically you can do concealed spaces in 4A and 4B with 2 layers of 5/8 inch type X direct applied to the mass timber. And in the 4C, you can have a concealed space if you put 1 layer of 5/8 inch type X gypsum direct applied. And again, I talked about this. Again, the high-rise sprinkler requirements kick in when you get over 120 feet. It means you have 2 water mains serving the building. And any GC that I've worked with that does high-rise, this has been nothing new to them. They're like, yeah, we do this all the time. What's the big deal? And so, or you valve a single main. And we've got a project in Seattle right now where we're having to valve the single main. That way you can pressurize the system from one direction or the other direction if the water line breaks in the earthquake. So CLT char fall off. I don't know if that's happened in your region. That happened here with some of the tall mass timber buildings. Nothing to worry about anymore. This went on for almost about 2 years. But basically now all the manufacturers use a heat resistant adhesive in their product, and CLT char fall off is not an issue anymore. But if it comes up, just let me know. And then connections, again, I mentioned this earlier. These are some of the connections we tested here for projects here in Portland. And so again, you've got to keep these fasteners out of that heat affected zone. Otherwise, this fastener will start charring from the inside out. We're putting in a fire caulk here on these connections in the tall buildings. Again, this stops the hot gas from getting in there and heating up that metal connection. So there's been lots of testing done, penetrations. Hilti's done an amazing amount of testing in there. Same thing here on these tall mass timber buildings. You have to put sealant at the panel edges. Again, what it's doing is it's stopping the hot gases from channeling up through these gaps and coming up to the next floor level. And this is what the IBC code says, is that you have to put the sealant in here. The funny part is, or you can go with a proprietary manufacturer's tested assembly that did not use sealant, and then you do not have to use sealant. But that puts you in bed with that proprietary manufacturer. And there are manufacturers that have gone out and tested these floor ceiling assemblies without sealant and passed the 2-hour test. So you start looking at a project, 18 stories, and it's like, wait, we can get rid of the sealant on 18 stories? That's money. So, but IBC, generic, prescriptive, you have to have sealant at the panel edges. And then the other hiccup that happens if you're doing some of these tall buildings is there's some fire protection under construction. And this is a bit onerous, especially with rain, is the big hang up here. And basically what they've said is once you get to the 5th floor, when required by 602 or 604.2, you have to put a layer of gypsum on. So if you're in a 4B, and your 4B says, hey, we've got 2 layers of gypsum on here for whatever reason, then once you get to this 5th floor, you've got to put at least 1 layer of gypsum on there. But you've still got this whole rest of the building to build, and it's raining. And so on one of our projects in Seattle right now, we're literally building a temporary roof every 4 floors to stop the water from getting into the building. So there are some fire protection under construction requirements. NFPA 241 is a good place to look for that, as well as IBC section 3313, IFC, the International Fire Code 3308 and 3313, or NFPA 241. All the requirements are in those sections for that. And that's that. So to answer a couple of questions that came in here, there's a picture of the well-spaced forest, seemed to have trees all the same height. Does that mean that that area was clear cut? Yes, you are correct. That area was clear cut. And then it was actually 3 trees were planted for every 1 tree they clear cut, but then they go and they thin the forest out. So that picture I showed earlier was right after they just finished thinning the forest out. Typically in the first 7 years time frame is when they would go and do that selective thinning. And then there's a question, is wood a superior building material for colder climates like in New England? Would steel or concrete building fare better with heavy load of snow or not? I'd say it's a non-issue, as you stated. The beauty of the wood, the mass timber, one of the cool things about it, wood is an insulator. So if you want to do like a cantilever, kind of like in this picture, if you want to do a cantilever out here, we can actually cantilever these beams out to pick up this awning out here, and you don't have to have a thermal break because the wood's an insulator. When you do steel, say you got a steel beam here, cantilevering out to pick up this awning, you should be putting in those neoprene decouplers there to stop the heat transfer of the steel going back into the structure. Whereas the mass timber can just go on out because it is an insulator. As for load-wise, you do need to take into account long-term creep. If you've got a long-term dead load on there, you should definitely be taking into account long-term creep effects. But as for like snow load and things like that, no. You look like you look at the UMass Amherst project. That UMass Amherst building has a green roof and an 11-foot design snow load on it. So for carrying the load and stuff, no. These engineered wood products, these engineered glue lamps and things like that, we can design those for whatever kind of load capacity that we need. Any other questions?
I think that was the last one we had. So Ethan, thank you very much for joining us today. Appreciate your time for sure. It was a lot of information packed into that hour. As a thank you, Rhode Island ASCE is going to be donating $100 to the Red Cross for Oregon wildfire relief. Pretty topical, related to today's presentation. And I want to let everybody know that our next event is planned for Thursday, February 18th. David O'Day is going to be presenting. He's going to give us an overview on some updates to ASCE initiatives and introduce an online beta test for Megacity as part of a Future World Vision project. So stay tuned for more information on that. If you have any other future topics that you'd like to see a presentation on or make a presentation on, reach out to us at riasce@gmail.com. And I'd like to thank Chad Morrison for helping coordinate and produce today's event behind the scenes. That concludes our presentation today. And again, please keep an eye open for future invitations, and thanks for joining us.